Cycloalkanes are named by counting the carbons in the cycle and ending the name with a cycloalkane. So this one is going to be a cyclobutane, and then naming the substituents on the cycle. If there is one substituent on the cycle, that substituent immediately is going to be on carbon number 1. It doesn't matter where the substituent is if it was only one substituent. So this is going to be an ethyl group. You skip number 1 or omit number 1. You don't write it in the name. So the name here is going to be an ethyl cyclobutane. Ethyl cyclobutane is all one word. This one here is going to be a methyl cyclopropane. Now, if you have a cycle with two substituents, so this is a substituent and this is a substituent here on the cycle, and the cycle is made up of 3 carbons, so your ending is going to be a cyclopropane. Now, these two substituents are different because this substituent here is a 1 carbon, so it is a methyl. And this substituent here is a 2 carbon, so it is an ethyl. You just arrange your substituents in alphabetical order and you give them the lowest number possible. Since E comes before the M, E needs to get the lowest number. So here I'm going to start numbering the ethyl from carbon number 1. And I'm going to go this way and name the methyl the second lowest number. So this is going to be carbon number 2 instead of going the other way and naming it as carbon number 3. So always give your substituents the lowest number or the lowest sum of numbers. So here it takes the lowest number and I arrange in alphabetical order. So the name is going to be 1 ethyl, 2 methyl cyclopropane. Here again, count the numbers of carbons in your cycle. So your ending is going to be in a cyclopropane. Now, since my 2 methyls here are the same, so I'm just going to go ahead and group them together, give them the lowest number. Because they are the same, I'm going to use the prefix di. So it's going to be 1, 2, dimethyl and cyclopropane. Now, if you have a cycle with the 3 substituents, this is a tri-substituted cycle. Count the number of carbons in the cycle. This is a 6 carbon, so that is going to be a cyclohexane. Put it at the end. Again, do not forget the word cyclo. Cyclo is a must. And now you're going to start by numbering your substituents in there. You want to give them the lowest number possible. So it makes sense you're not going to start from the center and number. You're going to start either numbering from this carbon or numbering from this carbon. And moving to the second substituent to give it the lowest number. So if I start numbering from here, this is going to be carbons 1, carbon 2, and carbon 3. And if I start numbering from here, then this is going to be carbon 1, carbon 2, and carbon 3. Notice that these are the same sum of numbers. 1 plus 2 plus 3, 3 plus 2 plus 1. They are the same sum of numbers. If you have this case, then you're going to go by alphabetical order. You have a methyl here. You have an ethyl there. The ethyl gets the lowest number, so this is why you have to start this way. And now your numbering is going to be 1 for the ethyl and 2, 3 for the dimethyl. So the name is going to be 1 ethyl, 2, 3 dimethyl cyclohexane. This is a tetra-substituted cycle. So again, count the carbons in your cycle. Your ending is going to be a cyclo. Let's start with the common name here. So the ending is going to be a cyclohexane. Now, with respect to our substituents, so what do we have? We have the isopropyl group. Since I am using the common, then I can do the isopropyl. I have my methyls in there, and I have my ethyl. So these are my 4 substituents. I want to give them the lowest number possible. So to give them the lowest number possible, I'm going to start numbering either from here or from here or from here. But it makes sense to number from this carbon because this carbon has the most number of carbons. So I'm going to end up getting the lowest sum of numbers if I start numbering from this carbon. So I'm going to start numbering from here 1. And I can go either 1, 2 here. It's going to be 3, 4, and 5. So my isopropyl is going to be on carbon number 2. And my ethyl is going to be on 5. Or I can go by 1 here and then 3 there. This is 4, 5, and 6. So do you see the difference there? I've increased the sum of numbers if I go this way. So I cannot go this way, so I'm going to stick to the first way. So I'm going to have isopropyl on the second carbon, methyls on the first, and then ethyl is going to be on the 5. Now let's arrange them in alphabetical order. The ethyl comes first. So this is going to be 5 ethyl. Now after the ethyl, I have the isopropyl because the I comes before the M. So I have 2 isopropyl, and then I have the 1,1, the dimethyl, and then the cyclohexane. Now with respect to the IUPAC, instead of naming the isopropyl in the common name, let's go ahead and name it in the IUPAC. And the isopropyl is going to be on carbon number 2. So just go ahead and open that and number the connection on carbon number 2. So let's use this color over here. So that is going to be carbon number 1. And this is going to be 2. And on 1, I have a methyl. So that is going to be 2, 1 methyl, ethyl. And let's go ahead and put it in alphabetical order. So to put it in alphabetical order, the E comes first. So we're going to start with 5, ethyl again. It's not necessary that the order is the same in the substituents when you want to name the common and the IUPAC, but here it happened. And then I do have the methyls come before the methyl ethyl. So I have the 1,1 dimethyl. We agreed that we're now going to consider the di in the naming. So we're going to drop the di and look at the M when we are alphabetizing. And then we have on carbon number 2, 1 methyl, ethyl. And then at the end, we have our cyclohexane. There is no space. Okay? Now, let's say, for example, if we have a substituent on the cycle, and that substituent has more carbons than that of the cycle. So see, your substituent is a 5-carbonate chain, and your cycle is a 4-carbonate chain. In this case, you cannot end your name in the cycle. So the cycle is not going to be the parent name. The parent name is going to be the chain because the chain has more carbons. So if this is the case, then your ending is going to be in pentane. And you want to give your cycle now because now the cycle is going to be now a substituent coming off this main chain. So you want to give it the lowest number possible. So to give it the lowest number, just go ahead and number that. If you number it from either ends, it's still going to be on carbon number 3. So the name here is going to be 3. It's going to be a cyclobutyl because it is a substituent after all. And all substituents have to end in a YL. And then your parent name is going to be pentane. There is no space between the cyclobutyl and the pentane. In this example, cyclohexane has less carbons than the 9 carbon branch that is coming off it. So this is why your ending has to be in the 9 carbons, not in the cycle. And the cycle is going to be a substituent. You're going to give it the lowest number because it's closer to the to one end of the chain, and you name the rest of the substituents. Here, you're going to give your substituents the lowest number possible or the lowest sum of numbers. It's both the same. So you can start numbering. If you start numbering from here, that is going to be a 1, 3, and a 4. And if you start numbering from here, this is going to be a 1, a 2, and a 4. A 1, 2, 4 is less than 1, 3, 4. So we're going to go with this way. It's going to be 1, 2, 4 triethylcyclopentane. There are substituents other than alkyl groups that you are responsible for. We're going to hit on all of these substituents, but for now, you're responsible for the alkoxy. You're responsible for the cyano, for all the halogens, how to name them. So if you have a halogen pointing off the main chain, you're just going to name it as a halo, like chloro, bromo, iodo, fluoro, etc. If you have an OR pointing off the main chain, something like this. So if you have an alkane chain, and if you have an O and a CH3, this is the OR, okay? So in this case, you're going to name it as an alkoxy. Alkoxy means this is a 1 carbon, so it's a methoxy. So you're going to name it as a methoxy, and you're going to give it the lowest number. So that is going to be 3-methoxy, and your parent chain in this case, this is 4, this is 5, and this is 6. So it's going to be a hexane. Okay. Another example here, if I have something like this, and if I have an O like that, and if I have a Cl, and if I have a bromine, and I ask you, go ahead and name that, then you're going to start by this end over here, because the bromine is closer to this end. You're going to give the bromine here the lowest number. This is 4, this is 5, this is 6, and this is 7. And you're going to arrange in alphabetical order. So that is going to be 2 bromo, 4 chloro, 5. It's going to be 2 carbons in there next to the oxygen. So it's going to be an ethoxy. And then it's going to be a heptane. So these you're responsible for. You're also responsible to name the NO2 substituent as well. The rest we're going to hit on those as we proceed with the course. There are other also alkane or alkene substituents that you are responsible to name. There are also other hydrocarbon substituents you are responsible to name. So let's say, for example, if you have an alkene hanging off the main chain. So this is a 2-carbon alkene, and it's hanging off the main chain. Then we are going to call this alkene a vinyl group. It's going to be a vinyl group. And the hydrogens that are on this vinyl group, we're going to call those vinylic hydrogens. So these are called vinylic hydrogens. Now, these hydrogens are very special because they are connected to 2 sp2 hybrid carbons. So I am expecting their sigma bond to be a strong bond. So these vinylic hydrogens are very hard to lose. This means that if you have a base in there, the base will not come and take any of these hydrogens. because the base cannot break that sigma bond. The allylic group is a group which is made up of 3 carbons. 2 of them are alkenes, and 1 of them is an sp3 hybridization. This is called an allylic group, and the allylic carbon is the carbon that is an sp3 hybrid carbon. So this carbon is called the allylic carbon. Now the allylic carbon has hydrogens in there, and these hydrogens, we're going to call them allylic hydrogens. These hydrogens are very easy to lose because they belong to an sp3 hybrid carbon. If you have a benzene connected to a CH2, we call that a benzyl. If you have just a benzene, we call it a phenyl group. So this is an example here, having the chloro, the nitro, and the methoxy. You just put them in the name and number your substituent. Give your first substituent the lowest number, arrange them in alphabetical order. C comes first, and then the methoxy, and then the nitrohexane. If you have a carbon chain, and on that carbon chain there is a benzene, we said that this benzene, we call it a phenyl group. So you're going to name this as 2-phenyl, and then octane. By the way, phenyl is abbreviated by a pH, so I can draw the chain like that, and on this carbon, I can put a phenyl. So if I want to name this is going to be 1, 2, 3, 4, 5, 6, 7, 8. Let's put it 9, 10. So this is going to be a 2-phenyl decene. If I have 2 substituents on the cycle, so let's say I have 2 CH3s on the cyclopropane. So this is going to be 1,2-dimethyl cyclopropane. Now these 2 substituents can either arrange to be in the same plane, meaning on the same side, or they can be on opposite sides. So there's 2 orientation for these substituents. Either they can be on the same side, and if they are on the same side, then I need to show them on the same side. Both of them can be either pointing up or they can be pointing down. Down is a dash and up is a wedge. And here I can see that these 2 substituents, they are on the same side. So if I have this case, then the substituents, with respect to each other, they're going to be in the same plane. So these are going to be cis substituents. So cis is going to be included in the naming. So to be more specific, when I name the 1,2-dimethyl cyclopropane, I have to put cis in there. And to do it, I put cis, then I put a dash, and then the 1,2-dimethyl cyclopropane. So cis indicates that the 2 substituents, which are the dimethyl on carbons 1 and 2, they are on the same side. And on the same side being either both they are up or both they are down. These 2 are the same. So being both up or both down is the same. The other arrangement of the dimethyl, they can be on opposite sides. And if they are on opposite sides, then I have to represent them, one of them being up, the other one is going to be down. These are going to be in different planes, or vice versa. One of them is going to be down, and the other one is going to be up. And again, those 2 are going to be the same representation. To name those, I need to differentiate them from substituent being on the same side. So these are two on opposite sides. To name them, I'm going to name them trans. And then trans what? It's the dimethyls that are on opposite planes. So it's going to be the 1, 2, the dimethyl, and then the cyclopropane. Now, cis and trans are different orientations of the substituents around the cycle in space. So these two are considered to be stereoisomers. So cis and trans are examples of stereoisomers, and by definition, stereoisomer is the orientation of the group in space. So the groups here can either be on opposite sides or they can be on the same side. So cis and trans, these are examples of stereoisomers. In our next chapter, we're going to talk about the different types of stereoisomers. One of the types of stereoisomers is cis and trans. And cis and trans, specifically, it's called geometrical isomers. So geometrical isomers is a type of stereoisomers, and stereoisomers is the orientation of the molecule in space. So when you have a cycle and you have two substituents on the cycle, not more than that, then these two substituents can either be on the same side or they can be on opposite side in there. So let's say, for example, if I have something like this, if I have a cyclohexane, and on the cyclohexane, I have a CH3, I have another CH3 in here, and I have a CH3 in there. Now, because I do have more than two substituents, so see, this is 1, 2, and 3. Whenever I name it, I cannot name it as cis and trans. So whenever I name this one, I just ignore the stereochemistry, meaning that the wedges and the dashes, I ignore those and I name it regular, giving the substituents the lowest number. So that's going to be 1, 2, and 4. So it's going to be 1, 2, and 4 trimethyl cyclohexane. I cannot say cis and trans because I have more than two substituents on the cycle. On the other end, if I have something like this, if I have the cyclohexane, and if I have my two CH3s, they are pointing up the cycle, something like that, okay? So now my substituents on the cycle are 2, not more than that. So now I can use the cis and the trans. And here my CH3s are on the same side. So the name is going to be a cis. Now it's going to be 1, 4. So that's going to be a cis 1, 4 dimethyl cyclohexane. Of course, I can use cis and trans for substituents that are different. So here the two CH3s are the same. I can have an ethyl, I can have a methyl. Let's have an example. So if I have a cycle, and if I have a CH3 here, and if I have an ethyl there, here you go. So in this case, I'm going to have start numbering from here because the ethyl gets the lowest number. And the name is going to be cis dash and 1 ethyl 3 methyl cyclohexane. So the term cis and trans, they exist only between two substituents. The substituents can be anywhere on the cycle, not necessarily on adjacent carbons. They can be anywhere on the cycle as long as they are only two substituents. And if these substituents are on the same side, we call them cis. And if they are on opposite sides, we name them trans. Cis and trans are examples of geometrical isomers, a type of stereoisomer where you have different orientation of the groups in space. So let's say, for example, if I ask you draw 1,2-dimethyl cyclohexane, if I didn't specify, then you have to draw the cis, you have to draw the trans isomer. Now the question here, which one is more stable? Stability has to do with energy. So the structure that has the higher energy is the least stable. And higher energy exists whenever substituents are close to each other. So here you have two CH3s, and those two CH3s, they are in the same plane and they are adjacent with respect to each other. So you're expecting those two to repel each other. So there's an energy between them. The energy is called a static energy or static repulsion. Static means that whenever you have bulky groups that are close to each other or groups other than hydrogens that are close to each other. CH3 here is not bulky, but CH3 here is not a hydrogen. So if you have two CH3s next to each other, they are going to repel each other. When they repel each other, the energy is going to increase and the stability is going to decrease. So always the cis isomer is considered to be less stable than the trans isomer. The trans isomer is more stable because it has less energy. The CH3s here, they are not in the same plane, so they won't repel each other. Energy here is less, so the stability is going to be more. So always the trans is more stable than the cis. Now geometrical isomers, the cis and the trans, they also exist in alkenes. So if you have an alkene, if you have a double bond, in order to figure out if the substituents around the double bond are on the same side or on opposite sides, the first thing that you do is you highlight the double bond. And then you look at the substituents that are the same. Here in this case, I do have my two hydrogens to be the same. So this is a hydrogen here and this is the hydrogen here. Now, if these substituents are on the same side, then we're going to call the stereoisomer cis. Again, highlight the alkene. And then look at the substituents that are the same around the alkene. And if the substituents are on opposite sides, here the hydrogens are on opposite sides, we're going to call this trans. To name the alkene, we're gonna go over naming simple alkenes now, and then once we hit the alkene chapter, we're going to explain naming in more details. To name the alkenes, always give the double bond the lowest number. So start numbering from the end to give the double bond the lowest number in there. Count all the carbons, including that of the double bond, and then drop the A and E of the alkane and add E and E at the end. Now, if your double bond is not at the end or on the first carbon, you have to locate where your double bond is in the chain. So here your double bond starts at carbon number 2, so it's going to be 2-pentane. Or you can name it as a cis, and it's going to be pent 2E. So you can include the 2 between the parent name and the ending, which is the functional group in this case. So here I know that my functional group is an alkene, or you can simply put the 2 in before the parent name, but that 2 indicates on what number the alkene is. When you want to name cis and trans and alkenes, you want to make sure that you have two substituents that are the same on adjacent carbons, not on the same carbon. So look here, my double bond is a terminal double bond. Terminal means it's at the end. So since it's a terminal, then in this case, I have my two hydrogens that are the same on the same carbon. This violates the rule for the cis and the trans and the alkene. To be cis and trans, you need to have two groups that are the same on adjacent carbons, not on the same carbon. So here I have no cis and trans. So when I want to name this, I name it as pentane. I drop the 1 because immediately when you say pentane, this means that the double bond is on carbon number 1.